Space looks calm. You see a photograph of a nebula, and it feels like silk and watercolour and quiet. The Milky Way stretching overhead on a clear night feels almost gentle. But hidden inside that beauty are events so violent that language breaks when we try to describe them. There are objects that could rip apart atoms, erase atmospheres, or outshine entire galaxies for a heartbeat. Our nervous system, built to worry about sharp rocks and hungry animals, has no idea what to do with that. Tonight we're going to gently stretch those fear circuits out to the scale of the universe. So if you enjoy journeys that make the cosmos feel stranger and your own life feel more precious, remember to like this video and subscribe. When we talk about cosmic danger, it is easy to drift into fantasy. Hollywood gives us planets exploding for dramatic timing, black holes that behave like vacuum cleaners, and asteroids conveniently aimed right at famous cities. The real universe is much weirder and far more patient. Out there, you find events that can release in a few seconds more energy than our star will produce in its entire lifetime. You find magnetic fields strong enough to tear apart matter, shock waves that sweep through galaxies, and beams of radiation narrow as a needle and long as the observable universe. The twist is that almost all of this happens unimaginably far away. That distance is both a blessing and a problem. For our ancestors, danger meant something close. A rustle in the dark might be a predator. A steep cliff might mean broken bones. Our brains are tuned to react to threats that are a few meters away, maybe a few kilometers at most. The universe does not care about that scale. When we say a star is nearby, we often mean it is tens of trillions of kilometers away. When we say a black hole is close, we might mean it is thousands of light years distant. Those numbers are so large that our emotional circuits never really wake up. There is another reason cosmic horror does not quite land. Most of these terrifying objects are indifferent to us in a very literal way. A supermassive black hole can sit in the center of a galaxy, shredding stars and launching jets of radiation, and Earth will never notice. A gamma-ray burst can sterilize the surface of a planet on the other side of its own galaxy, and for us it will be a faint flicker in a detector, our minds like villains with intent. The universe mostly offers us blind catastrophe, with no target and no anger. It feels like a horror story written in a language our instincts do not speak. Yet the facts themselves are astonishing. Our instruments have recorded storms on our own star that made telegraph wires spark and glow. We have measured flares from distant compact stars that briefly outshone entire galaxies in high-energy light. We have watched the sky flash in gamma rays powerful enough that, if they happened much closer, they could strip away an atmosphere. We have traced the shadows cast by invisible black holes and reconstructed the shapes of titanic jets of matter, moving at almost the speed of light. None of this relies on imagination. It is all drawn from real observations, real data, and real physics. So the question is not only what is out there, the deeper question is how we should feel about it. Do these discoveries mean the universe is hostile to life? Does learning about magnetars and rogue black holes and vacuum decay mean we should be more afraid? Or does it mean something else? Does it give us a new kind of comfort, a sense that we live in a fragile bubble of order surrounded by a vast wilderness that we can study but never control? Part of the adventure tonight is emotional. We're going to see whether we can expand our sense of fear without being swallowed by it. This is also a story about perspective and probability. Some of the objects we'll meet really could, in the right circumstances, wipe out life on a planet. Others sound terrifying but are functionally harmless to us because of the way space is arranged. We will talk about solar storms that absolutely can cause trouble for our technology, and hypothetical particles that almost certainly never will. When we say an event is rare, we will ask what rare really means in a universe with hundreds of billions of galaxies and trillions of planets. When we say something is unlikely, we will ask unlikely for whom and over what span of time. Along the way, we will keep one promise. This is not fear-mongering. We're not trying to give you nightmares. We're going to sit with the facts, take them seriously, and then ask what they truly imply for a small habitable world orbiting a quiet star in a calm spiral arm. Where danger is real, we will say so. Where the threat has been exaggerated or misunderstood, we will push back. The universe does not need help being dramatic. It is already more extreme than anything a movie studio could easily invent, and it stays that way even when we are careful with the numbers. To navigate this, we need a mental map. At the smallest scales, we have violent events tied to stellar death, compact objects, and nuclear-level densities. At intermediate scales, we have eruptive stars, planetary systems thrown into chaos, and wandering worlds cast into the dark. At the very largest scales, we have the structure of the universe itself and the question of how it will end. Everything connects. The same laws of physics that make a solar flare can, in more extreme environments, produce jets from a supermassive black hole or a gamma ray burst in a distant galaxy. The same gravity that holds you to the floor is what shapes clusters of galaxies across millions of light years. So where do we begin in this gallery of terrifying beauty? We could start with the most exotic objects, but there is something fitting about beginning at home. Before we face black holes and cosmic voids, we should get to know the star that quietly sustains every breath you take. It is stable on human timescales, dependable enough that ancient farmers counted on it without ever knowing what it was. Yet it is also a seething ball of plasma and magnetic fields that occasionally lashes out across the solar system. In our next step, we will move from the serene disk you see in the sky to the storms that rage on its surface, and the ways a single tantrum from our own star could reshape life on this planet for a long time to come. From Earth, the sun feels like the definition of reliability. It rises, it sets, it keeps you warm, and most days nothing dramatic appears to happen. Yet if you could hover above its glowing surface, you would see something closer to a slow riot than a calm fireplace. The sun is a churning sphere of plasma, charged particles and tangled magnetic fields, all in constant motion. It is only from 150 million kilometers away that this chaos averages out into a friendly yellow disk. To understand real cosmic danger that can actually reach us, we begin here, with our own star on a bad day. The sun is not solid. Different latitudes rotate at different speeds. Hotter gas rises, cooler gas sinks, and the whole body of the star behaves like a boiling magnetized ocean. All that motion winds and twists magnetic field lines like rubber bands. Where those twisted fields punch through the visible surface, you see dark freckles called sunspots. They are cooler than their surroundings, but only in a relative sense. Each one is still hotter than a blast furnace. Around clusters of these spots, stress builds as magnetic loops tangle and strain. Sometimes those loops snap and reconnect in a more relaxed shape. When that happens, the magnetic energy does not politely disappear. It erupts. A solar flare is the sudden release of stored magnetic energy in the sun's atmosphere. In minutes, it heats plasma to tens of millions of degrees and accelerates electrons and ions to high speeds. The flare floods space with X-rays and ultraviolet radiation and sends a surge of energetic particles racing outward. From Earth, a strong flare can cause brief radio blackouts and shake our planet's magnetic cocoon. But often the real trouble travels in a different form. Along with, or separate from, a flare, the sun can launch a coronal mass ejection. Imagine 1 billion tons of charged gas, threaded with magnetic fields being hurled into space. That cloud balloons outward, expanding and cruising through the solar system at hundreds to a few thousand kilometers per second. Most of these eruptions miss us entirely. Space is big, and Earth is small. But when one of these solar cannonballs is aimed just right, and Earth happens to be in the crosshairs, the impact is not physical in the sense of a punch. It is electromagnetic. Our planet's magnetic field takes the blow. The most famous example happened in the late summer of 1859. An English astronomer named Richard Carrington was sketching sunspots when he saw a sudden bright flash on the solar disk. Hours later, Earth's magnetic field reeled. Auroras flared bright enough that people in the Caribbean could read newspapers at night under shimmering skies. Telegraph systems sparked and failed. Operators reported getting shocks. In some places, even with the batteries disconnected, wires carried enough induced current that messages could still be sent. The world of that time was only lightly electrified. Yet a storm on the sun still reached down and forced itself into human technology. Now place that same energy into today's world. Modern civilization is wrapped in long conductors. Power lines stretch across continents. Undersea cables lace the ocean floor. Satellites orbit in fragile shells of electronics. When a strong coronal mass ejection hits Earth, it distorts the magnetic field and drives powerful currents in the ground and in any long wire. Transformers can overheat and fail. Voltage can surge through grids designed for calmer conditions. Satellites can be battered by charged particles and radiation, knocked into temporary amnesia or permanent damage. Navigational systems and communication networks can flicker or go dark. What was a nuisance in 1859 could be a serious global headache now. How often does a Carrington-scale storm happen? Solar physicists have to work with statistics based on a small sample. Historical records and ice core data suggest that storms of that magnitude are rare but not freakish, perhaps once every few centuries. There are hints of even larger events in the past. In 2012, a strong coronal mass ejection crossed Earth's orbit and missed us by about a week because our planet was on the other side of its path. If the timing had lined up differently, the 21st century would have had its own test of technological resilience. The point is not that doom lurks every year. The point is that cosmic weather occasionally throws a real punch. Then there is the bigger question that often fuels headlines. Could the sun fire off a true superflare? Telescopes like Kepler have watched other sun-like stars suddenly brighten by factors far beyond anything recorded on our star. These superflares release 10 to 1,000 times more energy than the largest flares we have seen on the sun. If something like that happened here, it could strip satellites, hammer the atmosphere, and possibly become a genuine planet-wide disaster. The comforting side of the story is that our sun seems to be a relatively well-behaved, slowly rotating star. Many of the stars that show superflares are younger and more magnetically hyperactive. That does not make superflares impossible here, but it suggests they are very unlikely on human timescales. Rather than panic, scientists treat the sun as a system to be monitored like weather. Spacecraft parked between the sun and Earth watch the star continuously. When they see a flare erupt and a coronal mass ejection launching toward us, they give us tens of minutes to a day or so of warning depending on speed. That is not a lot of time, but it is enough to take basic protective actions. Satellites can be put into safe modes. Astronauts on a space station can move to better shielded areas. Grid operators can adjust loads, temporarily reroute power, or even deliberately shut down vulnerable equipment to prevent more serious damage. Engineers are also learning how to harden infrastructure against solar storms. This can mean installing resistors in certain lines so that induced currents do not flow as freely, designing transformers that are more tolerant of geomagnetic disturbances, and creating regional plans for rapid restoration after an outage. These steps are not flashy. They do not make for dramatic movie scenes, but they turn a natural hazard from an existential threat into a serious but manageable problem. In that sense, a solar storm is closer to a 100-year flood than a cosmic death ray. You cannot stop it from happening, but you can make sure it does not sweep everything away when it does. Emotionally, solar storms live in an odd space. They are truly cosmic. They begin in magnetic knots the size of planets and unfold across millions of kilometers of plasma. Yet their effects show up as blown transformers, garbled radio signals, and disrupted navigation. They are where the majestic and the mundane collide. When auroras ripple across the sky in colours you never normally see, You're watching the visible side of a geomagnetic storm that might also be making grid operators sweat. It is drama written both across the heavens and inside the quiet hum of our electrical systems. By starting here, we have already met a phenomenon that can genuinely reach us, disturb our lives, and remind us that the sun is not a perfect, unchanging icon. And yet, compared to what else is out there, even a solar superstorm is a mild example of what the universe can do. The sun is a stable, middle-aged star. Some stars are not so calm. In the next chapter, we will leave the warmth of our own system and visit the corpses of massive stars. There we will find compact remnants whose magnetic tempers make solar flares look gentle, and whose brief outbursts can momentarily outshine entire galaxies. When a massive star dies in a certain way, it leaves behind something that should not really exist. Imagine taking a star many times heavier than the sun, stripping away its outer layers in a supernova, and then squeezing the leftover core down until it is no bigger than a city. The atoms inside are crushed, the gap between nuclei gone, matter packed so tightly that a teaspoon of it would outweigh mountains. That object is a neutron star, one of the strangest things the universe has ever built. Magnetars are the troublemakers in that family, the ones with magnetic fields so intense they almost rewrite the rules of what matter even is. To begin, picture an ordinary bar magnet on your fridge. Now picture the magnetic field of Earth, which is thousands of times stronger than that simple toy. The magnetic field at the surface of a typical neutron star is again trillions of times stronger than Earth's. For a magnetar, you have to stack another factor on top of that, turning up the dial until you reach the strongest stable magnetic fields known anywhere. These fields are not just numbers on a page, they are powerful enough to bend the paths of charged particles, twist the crust of the star, and even influence the behaviour of empty space. A neutron star forms when gravity wins a battle against pressure. Inside the collapsing core of a massive star, electrons and protons are squeezed together into neutrons. The core shrinks until the inward pull of gravity is balanced by the quantum mechanical stiffness of neutron matter. In that violent birth, magnetic field lines that once threaded a normal-sized star are dragged into a much smaller volume. Like squeezing the coils of a spring, compressing those field lines amplifies their strength. If the original star had strong magnetic fields and spun quickly, the result can be a neutron star whose magnetism is simply off the charts. That is a magnetar. Around a magnetar, atoms do not behave the way they do in a laboratory on Earth. In fields this strong, electrons are forced into tight spirals, and atomic shapes stretch out like spaghetti along magnetic lines. Photons can interact differently with the vacuum, a phenomenon called vacuum birefringence, where empty space acts like a crystal that bends and polarizes light. The surface of the magnetar is a kind of metal ocean, a crust of nuclei and electrons crushed into bizarre arrangements, with the dense neutron-rich interior beneath it. When the magnetic field shifts, that crust can crack. The star literally quakes. These star quakes are not gentle. Imagine the entire outer shell of a star-sized city shifting by a centimetre in a fraction of a second. The magnetic field, tightly anchored in the crust, snaps and rearranges. That sudden change hurls energy into the space around the magnetar. In a few tenths of a second, the star can release more energy than the sun does in hundreds of thousands of years. We detect these events as soft gamma repeaters and anomalous X-ray pulsars, which are technical names for neutron stars that burp out bursts and flares far in excess of normal pulsars. One of the most dramatic episodes happened in late 2004. A magnetar in our own galaxy woke up. It was about 50,000 light-years away, on the far side of the Milky Way. For a fraction of a second, detectors in orbit around Earth were slammed by a spike of gamma rays and X-rays so intense that some instruments saturated. The flash was bright enough that it briefly altered the ionization of the upper atmosphere on the hemisphere of Earth that faced it. A star the size of a city halfway across the galaxy, manage to reach out and stroke the skin of our planet with invisible fire. This sounds like the opening scene of a disaster story, but once we put numbers to it, the mood shifts. Even that enormous flare at that distance did not come close to killing the biosphere. It was a noticeable disturbance, not a planet killer. If a similar magnetar were only a few light years away, things would be different, but we do not see any such monsters lurking in our neighbourhood. Surveys of the sky and catalogues of nearby neutron stars tell us that magnetars are rare and tend to live in star-forming regions and crowded inner parts of galaxies, not in quiet suburbs like ours. There is another comfort hidden in the physics. Magnetars are born hot and excitable, but they age. Their rotation slows down as they radiate away energy. Those mighty magnetic fields gradually decay as currents inside the star rearrange. A magnetar is most temperamental in its first tens of thousands of years, which in cosmic terms is a brief tantrum in an otherwise long, cold life. After that, it relaxes into something closer to an ordinary neutron star. So even if a magnetar were to form in our galaxy, there is a limited window during which it behaves like a cosmic strobe light. Even so, these objects are not just curiosities, they are natural laboratories for physics that we cannot reproduce on Earth. In their cores, densities approach and may exceed those inside atomic nuclei. Neutrons might dissolve into their constituent quarks, or form exotic particles that only appear under such crushing pressures. Observing how magnetars spin down, how often they flare, and how their X-ray spectra look gives theorists clues about the equation of state of ultra-dense matter. The relationship between pressure and density at the edge of known physics. Each burst is both a fireworks show and a data point. Magnetars also teach us humility about what light can do. When their magnetic fields twist, they can launch beams and sheets of high-energy photons that travel for thousands of light-years almost unchanged. Somewhere out there, on a planet orbiting a star unlucky enough to sit close to an active magnetar, such a flare could be devastating. The upper atmosphere could be stripped, chemistry altered, life pushed back or erased. On those worlds, magnetars might truly be seen as cosmic demons. From our safe distance, we get the benefit of watching the demon roar without feeling its breath. Thinking about magnetars rewires our sense of scale in another way. They remind us that the quiet glow of the Milky Way on a clear night is not actually quiet. Scattered among those stars are corpses spinning dozens of times per second, magnetic hearts flaring and cracking, sending out pulses that sweep through space like lighthouse beams. We live in the same galaxy as those things, and yet have been untouched for billions of years. That contrast between potential violence and long-term safety will be a running theme in this journey. We started with solar storms, where danger is real but bounded by practical engineering. With magnetars, we stepped into a realm where the violence is almost artistic in its extravagance, yet cushioned by sheer distance and rarity. The universe is telling us something through them. It is saying that physics has a wild imagination, and that some of its most dramatic ideas are best appreciated from afar. In the next chapter, we will shift from compact stars that flare brilliantly to silent monsters that swallow light itself, drifting through space with almost no warning at all. Black holes have a reputation for drama. In movies, they roar, twist glowing gas into spirals, and tear spaceships apart. In reality, a typical stellar mass black hole is much less theatrical. Its event horizon might be the size of a small city. It has no surface to crash into, no glowing crust. It is just a region where gravity is won so completely that not even light can escape. The really unsettling part is this. Once you take away the bright disk of falling gas that sometimes surrounds them, a black hole is almost perfectly invisible. And some of them are not anchored to any star at all. They simply wander. Most black holes we know about announce themselves through their relationships. One might sit in a close orbit with a normal star and sip gas from its companion, heating that gas until it glows in X-rays. Others sit in the centres of galaxies and feed on whatever drifts too close, lighting up entire regions. A rogue black hole is different. It is a black hole that has been kicked out of any stable orbit and no longer belongs to any particular system. It just drifts through the galaxy on its own path, following a trajectory set long ago by violent gravitational encounters. There are a few ways to make such a wanderer. When a massive star explodes as a supernova and leaves a black hole behind, the blast is not always perfectly symmetric. If one side of the explosion is a bit stronger than the other, the newborn black hole can get a recoil, a kind of gravitational shove that sends it moving through space. In crowded star clusters, three-body encounters can also fling objects away. Two stars or compact objects in a tight pair can meet a third intruder. Energy gets exchanged, and often one of the trio is thrown out at high speed. If that ejected object happens to be a black hole, it becomes a rogue. Once set loose, a rogue black hole has no reason to stop. Space is nearly empty. There is nothing like air resistance to slow it down. It simply travels along a straight line through the Milky Way's gravitational field, curving slowly as it orbits the galactic centre. If it happens to pass through a region rich in gas, it might briefly light up by feeding, but most of the time it is just a moving patch of distorted space-time, dark against a dark background. That is part of what makes these objects so uncanny. They're among the most extreme things the universe can make, and yet they can be almost impossible to notice. So how many of these things are out there? Astronomers estimate that the Milky Way has formed enough massive stars over its lifetime to leave behind hundreds of millions, perhaps around 1 billion stellar mass black holes. Only a tiny fraction live in X-ray bright binaries where we can spot them easily. The rest are either quiet companions to faint stars or truly free floating wanderers. At first glance, 1 billion sounds terrifying. That is an enormous number. But remember how big a galaxy is. The average distance between ordinary stars in our region of the Milky Way is about 4 light years. That is 40 trillion kilometers of mostly nothing between suns. Even if there are hundreds of millions of black holes scattered through the disk, their average separation is still measured in many light years. You could drop our entire solar system between them and never touch a thing. Our own history backs that up. The planets have been orbiting the Sun in roughly stable paths for more than 4.5 billion years. If a rogue black hole had ever passed close enough to seriously disturb those orbits, the solar system would not look the way it does today. We simply would not be here to talk about it. The only reliable way to find a rogue black hole is to watch what its gravity does to light from other objects. When a massive compact object passes directly in front of a more distant star, its gravity bends the light in a very specific way. The background star appears to brighten and then fade in a smooth, symmetric curve. This effect is called gravitational microlensing. The shape and timescale of that brightening tell you about the mass and speed of the unseen lens. If the lens is dark and heavy and does not show any light of its own, you have a candidate for an isolated black hole. In the past few decades, large surveys that monitor millions of stars have begun to catch these microlensing events in real time. Most are caused by normal stars or white dwarfs drifting across our line of sight, but every so often, astronomers find an event that lasts long enough and is strong enough that only a very massive and very compact object fits the data. In one case announced in the early 2020s, follow-up observations with a space telescope measured not only the brightening of a background star, but also a tiny shift in its apparent position on the sky as the lensing object moved past. That subtle deflection revealed a dark object roughly 7 times the mass of the Sun, about 5,000 light-years away, drifting through the galaxy at around 45 kilometers per second. No star was visible at its position. There was no glowing gas disk, no burst of X-rays, nothing but gravity. It was the first strong, direct evidence that a solitary stellar mass black hole was out there, wandering through interstellar space with no companion. For decades, theorists had said such objects must exist. Now we could point with some confidence to one of them. Even that discovery does not make rogue black holes into villains. At 5,000 light-years away, This one poses no threat to us at all. It is simply following its orbit around the galactic centre, unaware of our existence. If a rogue black hole ever did pass through the outer reaches of a planetary system, the most likely effect would be a reshuffling of distant comets and icy bodies. Only an exceptionally close encounter with a planet would risk tearing it apart or flinging it free. The odds of that happening in any given system over the age of the universe are vanishingly small. There is a strange kind of philosophy hiding here. Rogue black holes represent cosmic indifference in its purest form. If one were ever to cross paths with Earth, it would not be angry or intentional. It would not be attacking. It would simply be continuing on a path written into its motion eons ago. You cannot argue with a gravity well. You cannot ask it to spare you. It does not care. And yet, from our vantage point on a safe, well-behaved planet, we can still find beauty in that. Because we have built instruments subtle enough to notice when a background star brightens by a fraction, or shifts its position by less than the width of a human hair seen from kilometers away, we can infer the presence of an object that emits no light at all. We have reached out into the darkness and traced the outline of something that would otherwise be completely hidden. That is a quiet triumph. The universe builds silent monsters. We build ways to see them. Rogue black holes are only one side of the story. They are small, stealthy products of stellar death. On the other end of the scale are black holes so massive that they anchor entire galaxies, surrounded by disks and jets bright enough to be seen across the observable universe. In the next part, we will travel from lonely wanderers in the dark to these supermassive engines in galactic hearts, and see how the same physics that makes a city-sized black hole also lights up quasars that can outshine trillions of stars. The black holes we have talked about so far are heavyweights by human standards, but they are still small in cosmic terms. A stellar mass black hole can weigh a few times more than the Sun, maybe a few dozen times more, and its event horizon can span a handful of kilometers. At the centers of galaxies, nature plays the same game on an absurdly larger scale. There you can find black holes with masses measured in millions and even billions of suns, big enough that their event horizons could engulf our entire solar system. These are supermassive black holes, and when they feed, they can turn whole galaxies into lighthouses. Our own galaxy is no exception. At the heart of the Milky Way, hidden behind clouds of dust and gas, sits a radio source known as Sagittarius A star. Astronomers have watched stars near this point whip around on tight, fast orbits, some completing a loop in only a few decades. By measuring those motions, they can weigh the unseen object they circle. The answer is startling. There is something there with roughly 4 million times the mass of the Sun, confined to a region no larger than our inner solar system. No cluster of normal stars could be that compact. The simplest explanation is a supermassive black hole. Most of the time, our central black hole is quiet. It nibbles on gas sporadically, flickers a bit, and otherwise minds its own business. In other galaxies, the story is different. When a supermassive black hole has a generous supply of gas and dust spiraling inward, the material does not fall straight in. It forms a swirling, flattened disk that orbits close to the event horizon. Friction, magnetic turbulence, and tidal forces inside this accretion disk heat the gas to enormous temperatures. The disk then shines across the spectrum from radio up through visible light and into X-rays. Here is the important twist. Accretion onto a black hole is one of the most efficient ways that nature knows to turn mass into energy. In a typical star, only a small fraction of the mass in the core ever undergoes nuclear fusion. In a thin, hot disk around a black hole, a sizable fraction of the gravitational energy of infalling matter is radiated away before the matter crosses the horizon. That means a relatively small amount of gas falling at the right rate can outshine all the stars in its host galaxy combined. From great distances, the starlight becomes background noise. The accretion disk dominates. These blazing central engines are called active galactic nuclei. When they are especially bright and far away, we often call them quasars, short for quasi-stellar objects. because early observations showed them as points of light that looked star-like through small telescopes. Their spectra told a different story. The lines of hydrogen and heavier elements in their light were shifted to longer wavelengths by enormous amounts, a signature of extreme distance and cosmic expansion. The only way to reconcile their apparent brightness with their distance was to accept that they are stupendously luminous. Each one can produce the light of 1 trillion suns from a region comparable in size to our solar system. Around some of these engines, something even more dramatic happens. Magnetic fields threading the accretion disk can wind up and focus some of the inflowing material into narrow jets that blast out from the poles of the spinning black hole. These jets fire streams of particles moving at speeds very close to the speed of light, carrying huge amounts of energy far out of the galaxy. If you view the system from the side, you see a bright core and, with powerful radio telescopes, twin jets reaching far into space. If one jet happens to point almost directly at Earth, you see something more extreme. You see a blazar. Blazars are active galactic nuclei with their jets aimed nearly along our line of sight. Because the jet material is moving toward us at relativistic speeds, its light is focused and boosted in our direction. This effect makes the source appear even brighter and more variable than it would otherwise be. Observers see wild, flickering in brightness over hours or days, and strong emission in high-energy gamma rays. In a sense, a blazar is a cosmic searchlight that just happens to be pointed at us from billions of light-years away. We are looking into the barrel of one of the most powerful particle beams in the universe, and yet we are safe because of staggering distance. For astronomers, quasars and blazars are not only spectacular curiosities, they are tools. Their intense light travels across cosmological distances and passes through clouds of gas on the way to us. Each cloud leaves its fingerprint as a pattern of dark absorption lines in the quasar's spectrum, especially from hydrogen. When you look at enough quasars in different directions, you see a kind of forest of these lines at different wavelengths, each corresponding to gas at a different distance and velocity. From that forest of imprints, astronomers can reconstruct the filaments of diffuse gas that thread the universe between galaxies. Quasars light up the skeleton of the cosmic web. Sometimes the path from a quasar to us is bent by gravity itself. If a massive galaxy or a cluster of galaxies lies along the line of sight, its gravity warps space-time and deflects the quasar's light. To us, the distant quasar can appear as multiple images, arcs, or even rings around the nearer lensing galaxy. These gravitational lenses serve two purposes at once. They magnify faint background objects, letting us study things we otherwise could not see, and they reveal the mass distribution of the lens, including dark matter that does not emit light. Once again, supermassive black holes become part of a chain of clues that lets us weigh and map the invisible. All of this might make you wonder how dangerous such a central engine would be if we lived much closer to one. If Earth orbited a star very near an active nucleus, the intense radiation and particle winds could strip atmospheres, disrupt planetary climates, and bathe surfaces in harmful high-energy light. Life might struggle to arise or survive under such a harsh sky. That is one reason why planetary habitability depends not only on distance from a star, but also on where that star lives within its galaxy. Quiet neighbourhoods far from the raging core are kinder to fragile chemistry. We are fortunate in that regard. The Milky Way's central black hole is relatively modest and currently underfed. From our location about 25,000 light-years away, its activity is a whisper. Astronomers do see echoes of a livelier past, like giant gamma-ray bubbles extending above and below the galactic plane, which likely trace ancient outbursts. But those events are over, and even at their peak they were not the kind of focused, narrow jets that would have roasted habitable worlds across half the disk. Our spiral arm is a suburb, and the downtown nightlife remains at a safe distance. There is something almost playful in the way the universe reuses ideas at different scales. The same equations that describe a stellar mass black hole swallowing gas also describe a monster like the one in the galaxy M87, with a mass of several billion suns, and a shadow big enough to swallow the inner solar system many times over. The first image from the Event Horizon Telescope collaboration showed that giant as a glowing ring around a dark centre, not unlike a scaled-up version of what a smaller black hole with a disk might look like. The universe seems fond of building gravity wells and then wrapping them in luminous costumes. By spending time with these supermassive engines, we have seen how the universe sometimes concentrates unimaginable energy into compact regions and then uses that light to sketch maps across billions of light years. We have also seen that, once again, the same distances that make these objects visible only as tiny smudges in our telescopes also protect us from their fury. In the next part of our journey, we will step away from steady engines and into the realm of sudden flashes, where collapsing stars and merging neutron stars fire off the brightest brief events the cosmos has to offer. These are gamma-ray bursts, and they are nature's way of showing just how extreme a single moment can be. In the middle of the Cold War, a group of satellites went up to watch for human weapons, and instead caught the universe misbehaving. The Vela spacecraft were built by the United States to monitor secret nuclear tests. Their detectors were tuned for the brief bursts of gamma radiation that accompany nuclear explosions in the atmosphere or in space. For a while, they did exactly what they were supposed to do. Then, in the late 1960s, the instruments began to see flashes that did not fit any expected pattern. They were too bright, too far away, and came from random directions in the sky. Someone, or something, was setting off cosmic gamma flashes. What followed was a slow, meticulous detective story. At first, the data were classified, because anything to do with nuclear monitoring lived behind locked doors. When scientists inside the program dug into the events, they noticed something strange. The bursts did not line up with Earth, the Sun, or the Moon. They came from all over the sky. That meant they were not coming from our planet at all. When the results were finally declassified and published, the astronomy community suddenly had a new mystery. Somewhere out there, far beyond the solar system, something was producing the most energetic flashes of high-energy light ever recorded. Today, we call them gamma-ray bursts. On a detector, a gamma-ray burst looks like a sudden spike in counts that can last from a fraction of a second to several minutes, followed by a fading tail. When enough had been observed, patterns emerged. There were bursts that lasted less than about 2 seconds, and bursts that lasted longer. The shorter ones tended to have harder, higher energy spectra. The longer ones were softer on average. That split hinted that there might be at least 2 families of events hiding under the same name, powered by different physical engines. Long gamma-ray bursts are now tied to the deaths of very massive stars. In some collapsing stars, the core does not merely trigger an ordinary supernova. It forms a black hole or a rapidly spinning neutron star wrapped in a dense infalling envelope. In that chaos, magnetic fields and rotation can focus some of the infalling material into twin jets that punch through the star and erupt into space at nearly the speed of light. As those jets plow into surrounding gas, they convert kinetic energy into high-energy photons. For a few seconds to a few minutes, the burst becomes the brightest single source of gamma rays in the observable universe. Short gamma-ray bursts appear to come from a different kind of catastrophe. When 2 neutron stars orbit each other in a tight binary, they slowly radiate away energy as gravitational waves. Over millions or billions of years, their orbit shrinks. Eventually, the stars merge in a violent collision. The outcome is again a compact central object, surrounded by debris and threaded by intense magnetic fields. Once more, jets can form and launch outward, beaming gamma rays in narrow cones. The same event also produces a kilonova, a slower, longer-lasting glow powered by the radioactive decay of heavy elements forged in the merger. Because gamma-ray bursts are so bright, we can see them from billions of light-years away. For a moment, a single jet can outshine entire galaxies. That intensity has a catch. The radiation is focused into narrow beams, as if nature were using a cosmic flashlight instead of a bare bulb. That beaming means we only see a small fraction of all the bursts that actually happen, namely those that are pointed roughly in our direction. It also means that the energy we infer from the brightness is spread over a much wider sphere when you account for all the directions the beam does not cover. Every few years, one of these events stands out even among its peers. On an October day in 2022, space telescopes around Earth lit up with alarms. They had caught a burst so bright that some instruments were overwhelmed. It came to be known by its catalogue name, GRB221009A, and was quickly nicknamed the brightest of all time. Light from that event had left its host galaxy more than 1 billion years ago, yet the gamma rays arriving now were strong enough to challenge existing models. The afterglow, the fading emission at lower energies, lingered and gave astronomers a rare detailed look at how such a blast evolves. When people hear about gamma ray bursts, a natural question arises. Could one of these things ever hit Earth and wipe us out? In principle, a burst close enough and pointed straight at us could strip away much of the ozone layer, letting in harmful ultraviolet light from the sun and stressing life on the surface. Some researchers have speculated that an ancient burst might have played a role in a past mass extinction. The evidence for that remains circumstantial and controversial. It is an intriguing idea, not a settled fact. What matters for our purposes is how likely such an event is today. The numbers, once again, are on our side. Gamma-ray bursts are rare in any given galaxy. Long bursts prefer low metal content environments, where very massive stars can form and retain their mass. Those conditions are more common in small, irregular galaxies and in the earlier universe than they are in a mature spiral like the Milky Way. Short bursts track old populations of neutron stars and can occur inside or outside galaxies, but known candidate systems are limited. On top of that, the dangerous zone around a burst is not the whole galaxy. It is a cone carved out by its jet, with a typical opening angle of a few degrees or less. Put all of that together, and the chance that a planet like Earth is sitting in exactly the wrong place, at exactly the wrong time, in the direct line of fire of a nearby burst, becomes incredibly small on human timescales. Over billions of years, the odds that some world somewhere is unlucky are high. Over a few million years in our local neighbourhood, the odds that it is this world are tiny. That is why gamma-ray bursts are thrilling to study and sobering to imagine, but not something that should keep you awake every night. They do, however, reshape our view of what is physically possible. When you realise that a dying star can rearrange itself into a machine capable of turning a substantial fraction of its remaining mass into a two-sided beam of pure energy, the word explosive feels too small. These are events where general relativity, nuclear physics, radiation transport and magnetohydrodynamics all collide. Simulating them pushes supercomputers to their limits. Observing them pushes our detectors to theirs. Each new burst is a test of our theories, and occasionally a challenge that forces us to revise what we thought we knew. There is also something quietly beautiful in their role as beacons. Because gamma-ray bursts are so bright, they can serve as backlights for the universe. Their afterglows pass through intergalactic gas and dust, picking up signatures that tell us about the composition and structure of matter across vast distances. Some bursts have been traced to galaxies so distant that their light left when the universe was only a fraction of its current age. Even in their violence, they act as flashbulbs illuminating the early cosmos. By now, our tour of dangerous cosmic events has included solar storms that threaten our power grids, magnetars that can jolt our atmosphere from across the galaxy, rogue black holes that drift unseen, and black hole engines that turn whole galaxies into searchlights. Gamma-ray bursts add another layer to that picture. They are the universe firing a starter pistol made of gamma rays, announcing the collapse of a star or the merger of two city-sized corpses. Yet, once more, distance, rarity, and geometry conspire to keep us safe. In the next part of our journey, we will slow down the timescale a little. Instead of a brief flash that is over in seconds, we will look at stellar deaths that unfold over days and weeks. We will meet hypernovae and the even rarer pair instability supernovae, explosions so complete that the star is not just transformed but entirely unbound. Where a gamma ray burst is a needle of energy, these events are vast, expanding bubbles of light and matter, rewriting their surroundings and forging heavy elements on a grand scale. Gamma ray bursts are like cosmic camera flashes. They blaze and fade in seconds. But some of the most extreme stellar deaths unfold more slowly, over days and weeks, as expanding bubbles of fire. These are the very brightest kinds of supernova, the ones that do not just disrupt a star but in some cases erase it. To understand them, we first need a picture of what a regular core collapse supernova looks like, and then we can turn the dial until it clicks past normal and into the realm of hypernovae and pair instability explosions. A normal massive star spends most of its life quietly fusing lighter elements into heavier ones in its core. Hydrogen turns into helium, helium turns into carbon and oxygen, and the chain continues up to iron. Each fusion step in that ladder releases energy that pushes outward against gravity. When the core fills with iron, the game changes. Iron does not give up energy when fused. The core can no longer support the weight of the layers above it. In a fraction of a second, it collapses. That collapse slams the core into nuclear densities. Protons and electrons merge into neutrons, and the inner region stiffens dramatically. The infalling layers bounce off this newly rigid core. Neutrinos burst out in unimaginable numbers, and some of their energy helps drive a shockwave back outward. The outer star is blown apart. For a few weeks, the dying star can shine as brightly as billions of suns. In the wreckage, a compact object remains, usually a neutron star or sometimes a black hole. That is the standard picture. Spectacular, but not yet the top of the scale. Hypernovae are core collapse events that seem to crank everything up. They're often linked to very massive, rapidly rotating stars that may have lost their outer hydrogen envelope. When such a star collapses, its spinning core and strong magnetic fields can transfer more energy into the outgoing shock and into jets that pierce the star. The result is a supernova that is both brighter and more energetic than average. In the sky, it can appear as a superluminous point of light that lingers and evolves in a way that standard models struggle to match without extra power. Evidence for hypernovae comes from carefully dissecting their light. The spectrum, the way brightness is spread across different colours, can reveal unusually high expansion speeds in the ejecta. That tells you the explosion had more kinetic energy than usual. Some hypernovae are found in the same places and times as long gamma ray bursts, suggesting they are two faces of the same underlying engine. The narrow gamma ray beam is the focused version that we see only when it points toward us. The luminous supernova is the broader, slower shell of debris that everyone in the surrounding region can see. As extreme as hypernovae are, they still leave a remnant core behind. Somewhere in the centre of the expanding cloud there is a black hole or a neutron star. Pair instability supernovae go a step further and remove the idea of a remnant altogether. In these events, the star does not just explode, it completely unbinds itself. No neutron star, no black hole, only an expanding cloud of gas and the memory of what was once there. To see how that can happen, we have to look at the balance of forces in the core of a truly enormous star. In very massive stars, radiation pressure is a dominant support. The star shines so intensely that the outward push of its own light helps hold up the weight of the overlying layers. Deep in the core, photons rattle around at energies so high that strange things become possible. When a gamma ray photon reaches a certain threshold, it can spontaneously transform into a pair of particles, an electron and its antimatter twin. That process steals energy from the radiation field and turns it into mass. The light that was helping hold the star up becomes matter that does not push outward in the same way. The result is a sudden loss of pressure. The core begins to contract. That contraction heats the gas even more, which in turn speeds up nuclear reactions, especially the fusion of oxygen. The extra fusion dumps more energy into the core in a runaway burst. Instead of settling into a smaller, denser equilibrium, the star detonates from the inside out. The nuclear energy released is so vast that it overwhelms gravity completely. Every layer of the star is accelerated outward. There is no chance for the core to reassemble into a compact object. The star simply tears itself apart. This kind of catastrophe does not happen to ordinary massive stars. You need a progenitor with a mass far above the usual range, probably well over 100 times the mass of the Sun, and with relatively few heavy elements in its outer layers. That combination makes pair production more likely, and reduces mass loss through stellar winds, so the star can keep enough bulk to reach the instability. The early universe, with its first generations of stars, was probably a better hunting ground for such monsters than the present day. Even now, we have found a handful of candidate explosions whose brightness and spectra hint that they might be modern echoes of this ancient process. In a pair instability supernova, the light curve, the way brightness rises and falls over time, can be broad and smooth. The star glows fiercely for weeks or months because there is so much radioactive material, especially nickel, created in the blast. As that nickel decays into cobalt and then into iron, it powers a long, bright afterglow. The amount of heavy elements forged in such an event is enormous. One explosion can enrich its surroundings with enough oxygen, silicon, and iron to seed many future generations of stars and planets. In that sense, these are not just destructive acts, they are creative too. What would it mean for a planet to sit near such a star when it goes? The answer is not pleasant. Intense light and high-energy radiation would wash over nearby worlds, stripping atmospheres and baking surfaces. A shockwave of gas would slam through the region, compressing interstellar clouds and perhaps triggering new waves of star formation. But there is that familiar word again, near. The zone of serious destruction is measured in dozens of light years, not across an entire galaxy. Beyond that, the explosion becomes another bright point in the sky, impressive but not personally dangerous. Here again, we are helped by the simple fact that stars big enough for hypernovae and pair instability explosions are rare. They live brief, flashy lives and tend to be born in dense star-forming regions, not in the quiet outskirts where stars like the Sun reside. Surveys of our local neighbourhood show no candidates that match the necessary profiles within the distance that would make them an existential threat. Over the lifetime of the Milky Way, many such giants have probably come and gone, but they did their work far from our current address. When you hear the words hypernova or pair instability supernova, it is easy to picture a pure doomsday machine. Yet if you trace the elements in your own body, you find that many were forged in the events not so different in spirit. The oxygen you breathe, the calcium in your bones, the iron in your blood, all owe their existence to violent stellar deaths. Some came from ordinary core collapse supernovae. Some may have been blown out by much more extreme explosions. Cosmic danger and cosmic generosity are intertwined. The same forces that can sterilize a region can also prepare raw material for future life. With hypernovae and pair instability events, we have explored the upper limit of what a single star can do to itself through nuclear burning and gravity. We have watched stars hold themselves up with their own light until that light betrays them, and we have seen how an entire stellar body can be turned into expanding debris. In the next part of our journey, we will leave the glare of explosive stellar death behind and step into the deep darkness between stars. There we will meet rogue planets, worlds with no sunrise at all, drifting through space as quiet, cold witnesses to all this surrounding violence. So far, every dangerous thing we have talked about has been anchored to something bright. Stars, black holes in galactic centres, jets blazing across the universe. Now we turn to a threat that is the opposite of that. No glowing surface, no gentle sunrise, no obvious warning in the sky. Just worlds adrift in the dark. These are rogue planets, also called free-floating planets, and they roam the spaces between stars the way icebergs drift through an ocean at night. A normal planet is born in a disk of gas and dust around a young star. Tiny grains stick together, grow into pebbles, then boulders, then moon-sized embryos. Those embryos collide, merge, and eventually become full-size planets. All of this happens within the gravitational embrace of the star. You would think that once a planet is built, it stays in its orbit forever. But gravity is not gentle, it is chaotic. When several large bodies dance around a star, their tugs on one another can, over time, throw one of them completely out of the system. Picture a young planetary system with several giant planets forming, all on intersecting orbits. They scatter each other, trading energy the way pool balls trade momentum. One may fall inward toward the star, another may move outward. In some cases, one of them is given so much energy that its orbit is no longer closed. It escapes. From that moment on, it is no longer a planet in the usual sense. It is a rogue world, carrying its moons if it had any, leaving its home star behind forever. Rogue planets can also be born from more dramatic events. If a star in a binary system swells into a red giant or explodes, its changing gravity can disrupt any planets in orbit. A passing star can yank planets away from another system during a close flyby. In crowded star-forming regions, young systems tug on one another so often that losing a planet may be a common outcome. The point is that there are many paths to exile. Given the age and scale of the Milky Way, those paths have had plenty of time to be walked. When astronomers ran simulations of how planetary systems evolve, a surprising pattern emerged. Ejection is not rare, it is expected. For every star that keeps a family of planets neatly bound, there may be other planetary bodies flung into space as the system settled down. Some studies suggest that there could be as many rogue planets as there are stars in our galaxy, perhaps even more, although the exact numbers are still uncertain. The Milky Way might be filled with dark, wandering worlds, each one almost invisible unless it happens to cross in front of something brighter. Detecting them is a challenge that pushes our methods to their edge. A planet on its own, far from any star, does not shine. It only glows faintly in infrared light as it slowly leaks away its internal heat. From our vantage point, that glow is drowned in the general cold hiss of space. Instead, we often look for the same effect we use to find rogue black holes. When a massive object passes precisely in front of a background star, its gravity bends and focuses the starlight. The star appears to brighten for a while. This gravitational microlensing does not care whether the lens is a star, a black hole, or a planet. It only cares about mass. By monitoring millions of stars in dense regions like the central bulge of the Milky Way, surveys have found brief microlensing events that seem best explained by objects with planetary masses and no detectable light of their own. These events are short, sometimes lasting only hours or days, because the lens is small and moves quickly across our line of sight. Each one is like the shadow of a drifting world, seen only in the way it momentarily tweaks the brightness of something far behind it. What would it be like to stand on a rogue planet? Start with the sky. There is no sun. Far away, some patch of the sky might contain a brighter band where distant galaxies or the Milky Way lie, but there is no daily cycle of day and night. At the surface, temperatures would plummet. Any atmosphere would collapse into ice if nothing else were heating the planet. The landscape would be a frozen desert, lit only by starlight and the faint, permanent twilight of the surrounding universe. It feels like the textbook definition of uninhabitable, yet physics likes loopholes. Inside a planet, radioactive elements decay and release heat. If the planet is large enough, that heat can be trapped under a thick layer of rock and ice. Under the right conditions, a rogue planet could have a subsurface ocean insulated by kilometers of ice, a bit like the oceans we suspect under the ice shells of moons such as Europa and Enceladus. Tidal flexing from any moons it retained could add extra warmth. From the outside, the world would look dead, Under the ice in the dark, there might be liquid water slowly cycling with chemistry that could, in principle, support life. There is a strange comfort in this idea. Even the loneliest objects in the galaxy may not be entirely sterile. Life, if it arises in such conditions, would never see a star. It would have no mythology of constellations, no concept of sunrise, no awareness that it is drifting through an immense structure full of light. It would simply know its local gradients of warmth and chemical energy. To that life, the universe would be the thickness of its ocean and the firmness of the ice above. The larger cosmos would be an abstraction it could never discover. From our perspective, the main way a rogue planet could matter is if it came near us. The mental image that often appears is dramatic. A giant dark sphere looms into the night sky, disrupting orbits, causing tides to rise, perhaps even colliding with Earth. Reality is far less theatrical. The solar system is large and mostly empty. To significantly disturb Earth's orbit, a rogue planet would have to pass very close, closer than the orbits of the outer planets. The odds of that happening in the current age of the solar system are so low that they are effectively zero on human timescales. A more plausible scenario is a rogue planet drifting through the distant outer regions, perhaps through the cloud of icy bodies thought to surround the solar system far beyond Pluto. There, its gravity could scatter comets, sending a few more than usual inward over millions of years. Even that is speculative. We have no evidence that such an encounter has ever happened. Our planetary orbits are stable, and the patterns of craters on the moon and planets do not scream of recent catastrophe on that scale. Once again, the universe provides the possibility but not the certainty of drama. As with rogue black holes, the real lesson of rogue planets is not that we should live in fear of them. It is that the architecture of planetary systems is more dynamic and more ruthless than it looks. The tidy diagrams you see in textbooks are snapshots, not full histories. Planets are born, migrate, and sometimes are thrown into the dark. The survivors, like Earth, are the result of countless gravitational coin flips that happen to land in a narrow range that allows stable, temperate orbits. By thinking about a world without a star, we also sharpen our appreciation of our own situation. Every sunrise becomes a reminder that we live on a world that kept its place, that did not get flung out into interstellar winter. Every stable season is a quiet echo of chaotic early times that have long since settled. The danger here is not imminent, but the perspective it offers is profound. A universe that can waste entire planets by tossing them into the dark and yet still, in some corners, build biospheres like ours, is a universe that mixes indifference and generosity in equal measure. In the next part of our journey, we will climb back up the ladder of violence. We will return to neutron stars, but this time in pairs that spiral together and collide. These mergers, called kilonovae, briefly turn tiny volumes of space into factories for gold and other heavy elements, sending out both gravitational waves and light. They are another example of how the universe uses its most extreme events not only to threaten, but also to create the ingredients that eventually end up in rings, electronics, and perhaps the device you're watching this on right now. When two neutron stars find themselves locked in orbit, the universe has quietly set the timer on one of its strangest fireworks shows. Picture a pair of city-sized corpses, each more massive than the sun, circling each other dozens or hundreds of times per second. They are so dense that they're gravity-dense space-time itself. With every orbit, they send out ripples, losing a little energy as gravitational waves. Slowly, over millions or billions of years, their dance tightens. The orbit shrinks, the frequency rises, the final minutes unfold in a frenzy. Gravitational waves are not like light or sound in air. They are literal stretching and squeezing of space-time that race outward at the speed of light. When they pass through Earth, distances between objects change by less than the width of a proton, then snap back. To catch that tiny effect, humans built observatories like the Laser Interferometer Gravitational Wave Observatory, with arms kilometers long and lasers bouncing back and forth in vacuum tunnels. For decades, this was a kind of heroic optimism. We were building ears for a kind of music we had never heard. In 2015, those ears first picked up the low bass note of two black holes colliding. It was a historic moment, but the signal came only in waves, with no accompanying light. 2 years later, in August 2017, something different arrived. The detectors felt a chirp that lasted for more than a minute, rising in pitch as two neutron stars spiraled together. Less than 2 seconds after the final plunge, space telescopes recorded a flash of gamma rays from the same patch of sky. Astronomers had been waiting for exactly this combination. They had caught a neutron-star merger in the act. The event was labelled GW170817. What followed was one of the most intense observing campaigns in the history of astronomy. Telescopes across the world and in orbit swung toward the source. In visible light, they saw a point in a distant galaxy brighten, change colour, and fade over days and weeks. At first it glowed bluish-white, then shifted into the red and near-infrared. That evolving light was the signature of a kilonova, a kind of explosion powered not by a shockwave from a collapsing core, but by the radioactive decay of freshly forged heavy elements. To understand why this happens, think about the conditions in the merger. When the neutron stars touch, tidal forces tear them apart. Streams of neutron-rich matter are flung outward at a fraction of the speed of light. In that ejector, nuclei are bombarded by neutrons at a furious rate. They capture neutron after neutron before they have time to decay, climbing the chart of elements into regions far heavier than iron. This rapid neutron capture chain is called the R process. Once the ejected material expands and cools, those unstable nuclei begin to decay towards stability, emitting energy as they go. It is that delayed release of energy that makes the kilonova shine. Among the products of this nuclear assembly line are some of the most familiar precious metals: gold, platinum, and rare earth elements that you find in the electronics, catalysts, and sometimes on human fingers are thought to be born in environments like this. For decades, theorists argued about where the R process happens. Core collapse supernovae were candidates, but the models had trouble producing enough heavy material. Neutron star mergers were another option. The light curve and spectra of GW170817's kilonova were strong evidence that at least a large fraction of the universe's gold and similar elements come from these collisions. There is a poetic short circuit here. Take your hand and look at any ring or piece of jewellery made from gold. Somewhere in its history is a moment when two dead stars collided in a distant galaxy. In a tiny, furious volume of space, nuclei were being slammed with neutrons, assembled into new forms and flung outward. Over eons, that debris cooled, mixed into gas clouds, and helped form new stars and planets. One of those planets eventually grew life, and some of that life mined the crust, refined the metals, and shaped them into symbols of love and status. When you trace it back, what looks like luxury is actually the fossil of a kilonova. Gravitational waves from such mergers also carry other kinds of information. By measuring how the signal from GW170817 changed over time, physicists could infer how easily neutron star matter squishes, a property called the equation of state. That tells us about the stiffness of matter at densities that no laboratory can reach. Comparing the arrival times of gravitational waves and gamma rays from the same event also lets scientists test whether gravity really travels at the speed of light, as general relativity predicts. With an experimental error, it does. One collision in a distant galaxy became a multi-purpose probe of fundamental physics. Of course, our theme in this series is danger as well as wonder. What would such a merger mean for a nearby planetary system? If you were close enough and unlucky enough to sit within the opening angle of the jet that powers a short gamma ray burst, the result could be harsh. High-energy radiation could strip away ozone and damage atmospheres. The kilonova's light, although brilliant, would be less of a direct threat than the focused jet. Over longer timescales, the radioactive ejector could bathe nearby space in particles and radiation. It is the kind of event that could reset the biological clock on nearby worlds. Once again, distance and rarity conspire in our favour. Binary neutron stars do exist in the Milky Way, and we have observed some as radio pulsars in tight orbits. By tracking their motion, we can calculate how long it will take for them to merge. The ones we know about are either far in the future of their inspiral, or far enough away from us that their eventual collision will be a spectacular light show, not a direct hazard. The overall rate of such mergers in our galaxy is estimated to be low, perhaps one every 100,000 years or so. On human timescales, that is almost forever. Even if a merger did happen in our galaxy within the next few millennia, the geometry would have to be just right for Earth to be in the narrow danger zone of its jet. Most bursts point their energy elsewhere. From the wrong angle, you would see only a bright but not lethal flare. From most angles, you would see nothing at all without a telescope. The universe is not aiming at us. It is just running through its own inventory of possibilities. Our role is that of a spectator who happened to build very good cameras. Neutron star mergers are a perfect example of the double nature of cosmic catastrophe. They are on one hand terrifying, involving density so high and energy so great that everyday language falls apart. On the other hand, they're creative engines that manufacture the stuff of planets and people. The same blast that could sterilize a nearby world is the one that allows other worlds, far away and much later, to form rocky crusts rich in metals and chemistry. When we study them, we're not just looking at distant explosions, we are looking at the origins of some of the most familiar materials in our lives. By following the trail from inspiraling neutron stars to ripples in space-time, and a sky that briefly changes colour, we deepen the sense that the universe is an ecosystem of forces rather than a static backdrop. Gravity, nuclear physics, and radiation are in constant negotiation. Out of their arguments come both hazards and the seeds of new structure. In the next part, we will leave the relative certainty of observed events and step into more speculative territory. We will ask what might happen if matter itself rearranged into a stranger form, and whether hypothetical substances like strange matter pose any real threat to ordinary worlds like ours. Up to now, every danger we have talked about has been dramatic in a familiar way. Explosions, flares, collisions, jets. Even if the scales are absurd, your mind can still picture something blowing up or smashing into something else. Strange matter is different. It is a threat that lives not in explosions, but in the idea that matter itself could prefer to be something else. This is where physics starts to sound like science fiction, and yet the questions are real enough that serious physicists have spent careers worrying about them. To follow the story, we have to zoom all the way down inside the particles that make up everything you see. Inside every proton and neutron in an atomic nucleus, there are smaller pieces called quarks. In normal matter, these come in two main flavours, up quarks and down quarks, held together by gluons in tight little triplets. A proton is 2 ups and 1 down. A neutron is 2 downs and 1 up. That is the simple picture. Quantum chromodynamics, the theory that describes quarks and gluons, says that under extreme pressures and densities, the neat structure of separate protons and neutrons might melt. Quarks could slosh around in a combined fluid instead of sitting in distinct particles. Neutron stars are the places where this is most likely to happen. In the cores of the most massive neutron stars, densities may be so high that the matter becomes something like a sea of quarks. At that point, it becomes possible that other quark types join the party. One of them is the strange quark, heavier than up and down, but still light enough to matter under such extreme conditions. If enough strange quarks show up, the mixture gets a new name: strange quark matter. Some theorists have suggested that this could be not just a weird state that appears temporarily, but the true lowest energy way for quarks to arrange themselves in bulk. If that is correct, then ordinary nuclear matter would be a kind of metastable phase. balanced on a ledge rather than in the deepest valley of the energy landscape. From that idea comes the nightmare scenario. Imagine a tiny lump of strange quark matter called a strangelet drifting through space. It bumps into an atomic nucleus, and because strange quark matter is more stable, it absorbs the nucleus and grows slightly. Each collision turns more ordinary matter into strange matter, like a crystal seed growing in a supersaturated solution. In a very dark version of this story, a single strangelet that lands in a neutron star could convert the entire star into one giant drop of strange matter. Carry the thought to Earth and you get an even harsher picture. A strangelet landing here could, in principle, chew its way through the planet, turning everything into a dense, hot lump, smaller than a city. If that sounds like the plot of a horror movie, you are not alone. The idea has shown up in fiction, in late-night conversations, and in anxious questions whenever humans build machines that slam particles together at high energies. The logic goes like this. If particle collisions can make exotic states of quark matter, could they accidentally make a strangelet that then eats the planet? When the Large Hadron Collider and similar facilities were being planned, teams of physicists had to take that concern seriously enough to write actual safety reports. The punchline of those reports is reassuring, and it rests on the universe itself as the ultimate test lab. Here is the key argument. Nature has been running particle accelerators far more powerful than anything humans can build for billions of years. They're called cosmic rays. High-energy particles zip through space and slam into each other, into stars, into white dwarfs, into neutron stars, and into planets at energies that dwarf our biggest machines. If it were easy to make a dangerous strangelet in such collisions, and if strangelets could convert normal matter in the runaway way imagined in the nightmare scenario, then dense stars hit by those cosmic rays should have been converted long ago. White dwarfs and neutron stars would have turned into strange stars. Planets might have been eaten. Yet we still see plenty of ordinary neutron stars and white dwarfs, and Earth is still here. There are also theoretical reasons to doubt the most dramatic version. Strange quark matter, if it is stable at all, is probably only favoured under conditions of enormous density and pressure. In a lab collision, matter is blasted apart into a hot, short-lived fireball that expands and cools rapidly. That is very different from the cool, compressed interior of a neutron star. Creating a stable droplet that survives and grows would require a very specific path through that chaos, and all the signs suggest that path is either impossible or wildly unlikely. Experiments at heavy ion colliders have looked carefully at the debris of these collisions. They have not found convincing evidence of strangelets lurking in the mess. That does not mean the whole idea of strange matter is nonsense. It just means that the most apocalyptic version is probably a dead end. The more measured possibility is that some neutron stars might indeed harbour cores where quarks, including strange quarks, roam freely. In that case, strange matter would be confined to those extreme environments, stabilised by gravity and pressure. It would not spread outward, eating everything. Instead, it would quietly sit in the heart of collapsed stars, changing their properties in ways we can only infer indirectly through their masses, radii, and cooling rates. This is where the story loops back to the role of extreme objects as laboratories. We cannot recreate the interior of a neutron star on Earth. It is too dense, too large, and too long-lived. But by measuring how fast a neutron star spins down, how it responds to tidal forces in a merger, and how hot its surface remains over time, we can constrain the possible forms that dense matter can take. If strange matter cores exist, they would leave signatures in these behaviours. Each new gravitational wave detection, each precise timing of pulses, tightens the net. The space of viable theories shrinks. Strange matter also exposes a deeper truth about where we sit in physics. The theory that describes quarks, quantum chromodynamics, is well tested in the regime of high energies and relatively low densities. It works beautifully in particle colliders. In the regime of cold, ultra-dense matter, the calculations become fiendishly hard. We are forced to use approximations and models that may or may not capture the full story. That is why ideas like strange quark matter appear. They are not wild guesses thrown into a void. They are honest attempts to map a part of theory space we cannot yet explore cleanly. Some of those attempts will turn out to be wrong. That is how science moves. From the point of view of cosmic danger, the conclusion is almost boring, and that is a good thing. There is no credible evidence that Strangelys are lurking in space, waiting to land on Earth and rewrite its atoms. There is no sign that the universe is filled with strange stars hiding behind masks of ordinary light. If strange matter exists, it is likely locked away deep in neutron star cores, where it will stay until the star itself is torn apart in a merger, and its contents are diluted back into normal space. The universe may keep some of its strangest phases carefully bottled. Yet even this non-eventful outcome changes how we feel about the cosmos. The fact that we can seriously discuss alternate ground states of matter and then rule out the most extreme consequences by looking at real stars and real data is a kind of quiet triumph. It means our understanding has grown to the point where our nightmares and our equations can talk to each other. The strange matter story reminds us that the universe always has more possible behaviours than we have yet imagined, but also that not every frightening idea survives contact with reality. With strange matter, we have walked up to the edge of what we know about the inside of things and looked over the side. We have seen how a hypothetical substance could, on paper, turn planets into dense marbles, and then watched as observations calmly told us that this does not seem to happen. In the next part of our journey, we will shift from the inside of matter to the ground beneath all of physics. We will talk about vacuum decay, the unsettling idea that even the empty space around you might not be in its most stable state, and what it would mean if the universe decided to roll into a deeper kind of nothing. Up to this point, our dangers have all been things in the universe: stars, black holes, bursts, worlds. Vacuum decay is different. It is not about an object drifting through space. It is about the stage on which everything happens. We usually treat empty space as a backdrop, a kind of neutral nothing that simply sits there while matter and radiation do the interesting stuff. Modern physics quietly insist that this is wrong. The vacuum has structure and energy, and in principle it could change. When you follow that idea to its conclusion, you end up with one of the strangest doomsday scenarios ever proposed. In quantum field theory, every type of particle is really an excitation of an underlying field spread throughout space. Even when you remove all the particles, the fields remain, humming with quantum fluctuations. The vacuum is the state of lowest energy those fields can settle into, or at least the lowest known energy. The key phrase there is lowest known. The equations allow the possibility that our current vacuum is not the absolute bottom of the energy landscape. It might be a local minimum, a comfortable but temporary resting place rather than the deepest valley. Physicists call such a situation a metastable vacuum. A common picture to make this feel less abstract is to imagine a ball sitting in a valley between hills. The valley is stable, small nudges do not move the ball far. But if there is a deeper valley hidden behind a higher ridge, the current resting place is only locally safe. In classical physics, the ball would stay where it is unless you gave it enough push to roll over the hill. In quantum physics, there is another option. The ball can tunnel. It can, with some tiny probability, simply appear on the other side of the barrier in the deeper valley without climbing over the ridge. If our vacuum is like that ball, then a patch of space could, in principle, spontaneously tunnel into a lower energy state. What would that mean in practice? In the theory, the tunneling shows up as the sudden appearance of a small bubble of true vacuum somewhere in space. Inside the bubble, the fields have new values, the energy density is lower, and as a result, the constants of nature can be different. The speed of light might be the same, but the strengths of forces, the masses of particles, the rules that govern chemistry, all could be altered. The surface of the bubble is a kind of expanding front where the old vacuum is converted into the new. That front races outward at close to the speed of light because there is no reason for it to stop. from the perspective of anything living in the old vacuum, this is the purest form of bad news. There is no warning, because nothing can outrun the front to tell you it is coming. There is no shelter, because the thing that is changing is the fabric of physics itself. One moment, atoms hold together, stars burn, and brains think. The next moment, as the bubble passes, those structures either become impossible or rearrange into something that does not resemble our world at all. There is no slow decay, no lingering agony. There is just the sudden replacement of one rulebook by another. If that sounds abstract enough that your fear circuitry does not quite know how to respond, you are not alone. Vacuum decay occupies a weird slot in the catalogue of possible catastrophes. It is absolute, in the sense that nothing we know could prevent or survive it. It is also almost certainly unimaginably remote in time, if it can happen at all. To say anything useful about the odds, we have to look at how our current theories describe a particular field that shapes the vacuum. That field is associated with the Higgs particle, discovered in 2012. The Higgs field is the thing that gives many fundamental particles their masses. Its value in the vacuum is not zero, and the shape of its potential energy curve helps determine whether our vacuum is stable or metastable. Using the measured mass of the Higgs boson and of the top quark, theorists can run the equations up to very high energies and see how the Higgs potential behaves. The surprising result is that, with current numbers, our vacuum sits near a boundary between stable and metastable. In simple language, it might be absolutely stable, or it might be perched in a long-lived, almost but not quite final state. The uncertainties in the measurements are still large enough that both options are on the table. If we are in the metastable case, does that mean we should expect vacuum decay soon? Not at all. The lifetime of such a metastable vacuum depends sensitively on the height and width of the energy barrier that separates it from the deeper state. The same calculations that hint at metastability also suggest that, if decay is possible, the expected lifetime is staggeringly longer than the current age of the universe. You can think of it as a radioactive substance with a half-life so long that not a single atom would be expected to decay in many trillions of times the current cosmic history. In that sense, the vacuum is effectively stable on any timescale that matters to stars, galaxies, or living things. There is another comforting argument, similar to the one we used for strange matter. High-energy cosmic rays have been smashing into each other, into stars and into compact objects at energies beyond those we reach in particle colliders, for billions of years. If there were some simple, low-barrier path to triggering vacuum decay through such collisions, it would likely have happened in some corner of the observable universe already. We do not see expanding spheres of altered physics eating galaxies. The sky looks statistically uniform and boring, which is exactly what you would not expect if bubbles of new vacuum were sweeping through space. Of course, vacuum decay could still happen purely by quantum tunneling, without any help from collisions. That is the dark charm of the idea. Even so, the fact that the universe has calmly expanded for billions of years without obvious signs of a transition is itself a kind of data point. It tells us that either the vacuum is fully stable, or the tunneling probability is so tiny that no such event has occurred within our observable patch of space-time. Either way, the risk on the kinds of timescales where we worry about supernovae or climate or civilizations is effectively zero. Emotionally, it is hard to know what to do with this. A nearby supernova or a large solar storm are dangers we can at least imagine taking precautions against. Vacuum decay offers no such comfort. If it happens, it happens. No warning, no plan, no legacy. Some people find that notion horrifying. Others find it oddly calming compared to slower scenarios where the universe fades gradually into darkness. You will never see it coming, and neither will anyone else. There is no suspense, no countdown, only the knowledge that physics might have one more trick built into it that will never actually fire in our lifetime. Philosophically, vacuum decay pushes us to rethink what we mean by law and by permanence. We like to believe that the constants of nature are fixed, written once at the birth of the universe. The very concept of a false vacuum says that even those constants may be part of a phase, a chapter, rather than the whole book. The possibility of transition does not make our current chapter less real. It simply reminds us that even the deepest rules we know may themselves sit on something deeper and more flexible. In that sense, vacuum decay is less a threat and more a mirror held up to the limits of our understanding. By walking through this scenario, we have stretched our imagination from explosions and jets all the way to the foundation of space-time. Along the way, we have learned that some theoretical nightmares are diffused by careful calculation and by the simple fact that the universe has persisted in its current form for a very long time. In the next part of our journey, we will zoom back out from the microscopic details of fields to the grand architecture of the cosmos. We will look at how matter and emptiness arrange themselves into a vast web of filaments and voids, and what it really means to live in a universe where most of the volume is, in every practical sense, nothing at all. From Earth on a dark night, the universe looks pleasantly crowded. The Milky Way arches overhead as a dense band of stars. Through a small telescope, galaxies pepper the sky. It feels as if the cosmos is full in every direction. But if you could somehow step back and see everything at once, you would discover a very different picture. You would see that matter is not spread out evenly. It is arranged in a vast, ghostly network, and most of the volume is almost unimaginably empty. Astronomers began to glimpse this structure when they mapped galaxies in 3 dimensions. Instead of just taking images, they measured distances and plotted where each galaxy sits in space. The result was not a smooth fog of points. It was more like foam or a sponge. Long filaments of galaxies stretched across space. At the intersections of those filaments sat clusters, great knots of hundreds or thousands of galaxies bound together by gravity. Between the filaments lay enormous regions where almost nothing seemed to exist. Those deserts are called cosmic voids. The whole pattern is known as the cosmic web. It is shaped by gravity acting on dark matter, the invisible mass that outweighs normal matter by a large factor. In the early universe, small fluctuations in density grew over time. Regions that were slightly denser pulled in more matter and grew denser still. Regions that were slightly emptier lost material to their neighbours. Over billions of years, this feedback sculpted a network of sheets and filaments, with matter flowing along them toward the nodes where clusters now sit. Galaxies formed along these structures like beads on strings. Voids, in contrast, are the places that lost the tug of war. They started only a little underdense and ended up almost completely swept clean. A typical large void can span hundreds of millions of light years across. Within that volume, there may be only a few lonely galaxies. The most famous example is the Bootes void, a roughly spherical region discovered in the 1980s that contains far fewer galaxies than you would expect by chance. When astronomers first mapped it, it looked like someone had carved a hole in the universe. Try to imagine living in a galaxy deep inside such a void. Look up at the night sky from a planet there, and your home galaxy would still be filled with stars. You would still have a Milky Way of your own overhead. But when your telescopes grew powerful enough to look beyond, the view would be strikingly different from ours. Instead of a sky crowded with thousands of other galaxies, you might see only a handful of faint smudges. The cosmic web would still exist. You would just be sitting far from its brightest threads. From that vantage point, the very idea of a rich universe might be harder to discover. You could point your instruments in all directions and find darkness and a few scattered islands of light. You might conclude that you live in a small, mostly empty cosmos, with your galaxy almost alone. Only with extremely sensitive observations would the faint glow of distant filaments and clusters begin to appear. In a sense, observers in a void have a distorted picture of reality, not because their data are wrong, but because their cosmic address is so isolated. We, by contrast, live in a moderately dense region of a fairly typical filament. Our local group of galaxies sits on a thread of the web that is itself part of a larger supercluster region. When we map the sky, we see many clusters, filaments, and walls of galaxies. We also see gaps, but not the vast, cavernous emptiness of the largest voids. That relative richness makes it easier for us to infer the web-like pattern. It also tempts us to forget how special our location is. On the larger scales, emptiness wins by volume. Dark matter underpins all of this. Although we cannot see it directly, we can measure its influence. Galaxies and clusters move too fast to be held together by visible mass alone. Gravitational lensing reveals extra mass along filaments. Computer simulations that start with a smooth distribution of dark matter and let gravity do its work naturally produce a cosmic web that looks very much like the one we observe. In those models, normal matter falls into the wells carved by dark matter and lights them up with stars. Voids are the regions where the wells are shallowest. Cosmic voids are not merely empty footnotes. They are sensitive probes of cosmic expansion and of dark energy, the mysterious driver behind the accelerated growth of the universe. As space expands faster, matter drains more efficiently out of underdense regions. Voids puff up and become rounder. By measuring their sizes, shapes, and how galaxies move around their edges, astronomers can test models of dark energy and gravity. The most boring possible result, a simple, smooth acceleration, is still the frontrunner. But even that boring answer has profound consequences for our future. If the current trend continues, galaxies that are not gravitationally bound to us will drift farther and farther away. Light from them will be stretched to longer wavelengths and eventually slip beyond what our instruments can detect. Over many tens of billions of years, the cosmic web as we see it today will fade from view. Distant filaments and clusters will slide over the horizon, defined by the speed of light and the rate of expansion. To far future observers in our galaxy, the universe will look more and more like a lonely island of stars in a featureless dark sea. In that sense, the largest voids you see now are previews of the eventual mood of the cosmos. Their vast emptiness, broken only by a few galaxies, is a snapshot of what the entire observable universe will one day resemble from any one point. The difference is that, in the future, there will still be structure out there. It will just be unreachable and invisible. Space will not have become simpler, it will have become harder to see. Our current era, with its rich view of the cosmic web, is a kind of observational golden age. All of this reframes our earlier talk of danger. The universe can be violent on local scales with exploding stars, flaring magnetars, and merging neutron stars. On the larger scales, though, the dominant feature is not violence. It is emptiness. Vast stretches of space where nothing much happens for billions of years. Out there, the main threat to life is not being hit by anything. It is being too far from sources of energy and complexity to ever arise in the first place. We live in a rare overlap, a place where there is enough matter for structure and enough emptiness for long-term stability. By tracing the cosmic web and peering into its voids, we have seen how structure and nothingness weave together to make the universe we inhabit. We have also glimpsed a future in which that visible structure slowly slips away, leaving later astronomers with a much lonelier sky. In the next part of our journey, we will look further ahead still. We will ask how all of this ends, following the threads of entropy, dark energy, and gravity into scenarios where the last stars burn out, black holes evaporate, and the cosmos itself either fades into heat death or tears itself apart. We have spent most of this journey asking, what could go wrong for life in the near and middle future of the universe? Supernovae, flares, bursts, mergers. Now we're going to do something more unsettling. We're going to ask what happens when you let the clock run all the way forward, not just 1 million years or 1 billion years, but as far as physics can reasonably see. In that distant horizon, the threats are not single explosions or passing objects. The threat is that the universe itself simply runs out of ways to stay interesting. At the heart of this long view sits a single idea called entropy. In simple terms, entropy measures how spread out and mixed up energy is. A hot cup of coffee in a cold room has low entropy compared to the room plus coffee Once everything has reached the same lukewarm temperature, the universe started in a very low entropy state, with matter and energy arranged in a surprisingly orderly way. Over time, processes like star formation, radiation, and mixing push it toward higher entropy. More spread out, more uniform, less structured. Heat death is the name for what happens if you let that trend run to its logical end. Imagine a universe where every useful temperature difference has been smoothed out. No more hot stars and cold space. No more dense galaxies and thin voids. Instead, everything is close to the same temperature everywhere, and almost all the energy is in low-grade, thinly spread radiation. In that state, you can no longer run engines, build complex structures easily, or sustain the kind of organised flows that life seems to need. The universe is not dead in the sense of frozen, it is dead in the sense of boredom. Nothing much happens. Getting there takes an absurd amount of time. First, ordinary stars have to burn through their nuclear fuel. The smallest red dwarfs can shine for trillions of years, far longer than the universe has existed so far. When they finally fade, you're left with a sky filled with stellar corpses. White dwarfs, neutron stars, black holes, and cold planets. Over even longer spans, white dwarfs slowly cool and dim, turning into black cold cinders. The galaxies we know now become dim swarms of embers. We can go further. Many theories beyond the simple standard model of particle physics predict that protons themselves are not truly eternal. If proton decay is real, then over a fantastically long time, the very atoms in dead stars and planets will occasionally fall apart. A proton might survive for a time longer than a 1 followed by 30 or 40 zeros in years, but given enough time, even that decay becomes important. Solid matter melts down into a thin soup of lighter particles and radiation. If protons are actually stable, the story changes in detail, but not in mood. Gravity still slowly rearranges matter and radiation into more diffuse forms. Black holes, which at first glance look like the ultimate garbage bins of the universe, are not safe either. Stephen Hawking showed that quantum effects near the event horizon should make black holes leak energy very slowly as radiation. This process, called Hawking radiation, robs them of mass bit by bit. Small black holes evaporate quickly on cosmic scales. Supermassive black holes take longer, enormously longer, but even they eventually shrink and vanish in a final faint hiss of energy. After enough time has passed, the last black hole in the universe disappears. Now picture what is left. A vast, almost completely empty space filled with extremely thin, extremely cold radiation, and a scattering of low-energy particles drifting with no particular direction. There are no more stars to form, no more black holes to anchor galaxies, no dense lumps left to power anything. On human scales, that universe might as well be nothing. There is simply no way to assemble something as complex as a cell, let alone a brain or a civilization. That is heat death. It is not a dramatic bang. It is a slow fade into uniformity. Heat death is the current favourite in the list of possible endings because it fits well with what we see. The expansion of the universe is speeding up, driven by something we call dark energy. If that acceleration stays gentle and steady, then galaxies that are not tightly bound to us will drift beyond our horizon. Star formation will slow as gas is used up. Entropy will keep climbing. Nothing in that picture suggests a sudden reversal. It suggests a long, quiet unwinding. But dark energy is still mysterious, and that leaves room for other fates. One alternative is the Big Rip. In this scenario, the force driving cosmic expansion does not remain constant. It grows stronger over time. At first, it behaves like the ordinary acceleration we infer today, pulling clusters and superclusters of galaxies farther apart. As it ramps up, it begins to overcome the gravity that holds galaxies together. Then it overcomes the gravity that binds stars to galaxies, then the gravity that holds planets to stars. In the final stages, Even molecules and atoms are torn apart as space itself stretches faster and faster. The universe ends not in cold uniformity, but in a kind of shredding. There is also the old idea of a big crunch. If dark energy were to reverse sign or vanish and gravity had the upper hand, the expansion of the universe could slow, stop, and reverse. Galaxies would begin falling back toward one another. The cosmic web would collapse. Temperatures would rise as matter compressed. In the most extreme forms of this picture, everything ends in a final dense state where the distinction between inside and outside loses meaning. Some versions imagine that this state could bounce, setting off a new expansion and perhaps a new cycle of cosmic history. Right now, the evidence points away from this story, but it remains a logical possibility in some models. There are even more exotic proposals. Some suggest that dark energy could undergo sudden changes, triggering phase transitions that reshape the fate of the universe. Others involve extra dimensions or multiverse-style scenarios where our observable cosmos is just one bubble among many. In those pictures, what we call an ending might look like a minor event in a larger, stranger structure. For now, these ideas live more in the realm of theory than data. They are reminders that our understanding, while powerful, is still incomplete. From the standpoint of a civilization, the details of which ending we get matter less than the shared message they all carry. The era in which stars shine and galaxies are visible, and chemistry is rich, is temporary. We live in what some physicists call the stelliferous age, a time when nuclear fusion powers light and heat across the cosmos. That age will not last forever. Whether the universe fades, rips, crunches, or does something we have not yet imagined, the window for life as we understand it is finite. Does that make everything feel pointless? It can, if you lean into the bleakness, but there is another way to read the story. The fact that the universe will not always be hospitable to complexity makes the present more rare, not less meaningful. You're alive in a period when the night sky is still full of galaxies, when the laws of physics allow stable atoms, warm planets, and the slow, improbable climb from simple molecules to self-aware beings. Against the backdrop of heat-death timescales, the entire history of life on Earth is a brief flicker. Yet within that flicker, entire worlds of experience, culture, and meaning have bloomed. It also reframes our earlier catalogue of dangers: supernovae, magnetars, gamma-ray bursts, rogue planets. All of them are violent on human scales and geologic scales. On the scale of the universe's full timeline, they are tiny adjustments, temporary rearrangements in a cosmos that is marching toward much more profound changes. That does not make them unimportant, it just places them in a broader frame. The universe is not out to get us. It is simply following its own rules, on timescales much longer than any living creature will ever see. With the ultimate fates on the table, you might expect the end of this story to be hopeless. Instead, the last steps of our journey will curve back toward comfort. In the next part, we will pull together everything we have seen and ask what really shields us from most of these dangers. The answer is not a force field or an ancient guardian. It is something much simpler and more surprising: distance, emptiness, and statistics. We will see how the same vastness that makes the universe feel lonely is also the reason you can sleep at night on a small planet around an ordinary star. After a long tour of cosmic horrors, it is easy to feel as if the universe is a minefield, and we're just lucky not to have stepped on anything yet. Magnetars, rogue black holes, gamma-ray bursts, vacuum decay. Each one sounds like a story designed to keep you awake at night. Yet if you step back and look at the big picture, a quieter pattern emerges. Most of the things we have met are real. Most of them can be dangerous, and almost none of them ever come close. The reason is hidden in the thing our brains are worst at feeling directly: distance. Human intuition evolved in a world where distance meant meters and perhaps a few kilometers. If something loud or bright is that far away, it is probably relevant to your survival. If a predator is 10 meters away, you care. If a thunderstorm is a few kilometers away, you keep an eye on it. Our instincts never had to deal with threats that are trillions of kilometers away. So when we toss around words like light year, our emotional response flatlines. It feels abstract, not protective. That is a mismatch we need to correct. Start with a simple comparison. The distance from Earth to the Sun is about 150 million kilometers. Light covers that in about 8 minutes. The distance to the nearest star beyond the Sun is a little over 4 light years. That is roughly 40 trillion kilometers. In terms of danger, that gap is enormous. Solar flares and coronal mass ejections can and do hit us because we are tethered to our star at close range. The nearest stars are so far away that even if one of them exploded in a spectacular supernova tomorrow, its main effect on us would be an extra bright point in the night sky. The intense part of its radiation would spread out over a sphere so large that Earth would barely notice. That same logic applies all over the cosmic catalogue. Magnetars can jolt our upper atmosphere from tens of thousands of light years away with a rare giant flare. To turn that disturbance into a true extinction-level event, you would need a magnetar to be not just in our galaxy, but relatively close, within a few light years, and pointed at us during its most active phase. We do not see any such object in our neighbourhood. Gamma-ray bursts are even more narrowly aimed. Their jets carve out tiny cones in space. To be hit hard by one, your planet must be both uncomfortably close and sitting inside that narrow cone at the exact moment of the burst. On paper, it can happen. In a galaxy with hundreds of billions of stars, the probability that it happens to you during the brief window when you exist is tiny. Another way to feel this is to think in terms of volume. Picture a sphere around Earth with a radius of 10 light years. It contains a few dozen stars. Now picture a sphere with a radius of 1,000 light years. The volume has grown by a factor of 1 million. A magnetar flare or a supernova or a neutron star merger happening somewhere in that larger sphere will almost always be too far away to be more than a signal in our detectors. When astronomers talk about an event being in our galactic neighbourhood, they often mean many thousands of light years distant. That is close for astronomy and unimaginably far for biology. The universe also hides us through emptiness as much as through distance. Space is not filled with a smooth fog of stars and planets. As we saw in the cosmic web, most of the volume is void. Even inside a galaxy like the Milky Way, space between stars is vast and mostly empty. Rogue black holes wander, but they are separated by light years. Rogue planets drift, but they rarely approach a star closely. To threaten a particular world in a dramatic way, an object has to thread a needle in phase space, passing through a very small region of all possible positions and velocities. There is a near infinity of paths where nothing bad happens, and only a vanishing subset where things go really wrong. Our specific address adds another layer of protection. The Sun lives in a calm spiral arm, far from the crowded core of the galaxy, far from big star-forming regions where massive, short-lived stars blow up in clusters. We're not orbiting inside a dense globular cluster where close stellar encounters are common. We're not circling close to a supermassive black hole that is actively feeding. The local neighbourhood is more like a quiet suburb than a city centre. That quietness is not an accident. Stars like the Sun that live long enough to let complex life evolve tend to form and survive in such peaceful regions. Statistics also play a role that is easy to miss. If there are trillions of planets in the observable universe, then somewhere, right now, one of them is probably being sterilized by a nearby burst or bathed in radiation from a hyperactive nucleus. Somewhere, a rogue planet might be plunging through an inner system, or a magnetar flare might be stripping the atmosphere off a world that was just starting to grow forests. Those events are tragic on a local scale. On the scale of the whole universe, they are simply part of the background noise. We are disturbed by them because we imagine being on those worlds. The actual probability that we are on those worlds is tiny. Our fear circuits, however, do not operate on probability. They operate on vividness. A story about a single asteroid hitting Earth sticks in the mind more than a chart showing that for billions of years the planet has quietly orbited without major catastrophe. A word like extinction feels heavy, even if the event that would cause it has a 1 in many millions chance of happening in any given century. The universe does not care about what feels scary. It only cares about what actually happens often. Solar storms and moderate asteroid impacts happen often enough that it makes sense to prepare. Vacuum decay, galaxy-destroying gamma-ray bursts aimed exactly at us, or close passes by rogue black holes do not. One of the healthiest ways to live with this knowledge is to separate existential fear from practical concern. It is reasonable for a civilization to invest in monitoring the sun, tracking near-Earth asteroids, hardening its power grids, and preparing for storms that statistics say will eventually arrive. It is not reasonable to lose sleep over speculative events that have not happened once in the entire history of our planet, despite constant bombardment by cosmic rays and 4.5 billion years of cosmic lottery tickets. Distance and emptiness are not perfect shields, but they are very good ones. In a strange way, the same vastness that makes the universe feel lonely is exactly what keeps it from being constantly lethal. If stars were packed 100 times closer together, if galaxies were dense swarms instead of thin disks, the night sky would be spectacular and the hazard rate would be much higher. Explosions, flares and jets would have less room to fade before they hit something important. We live in a compromise universe, one where there is enough matter for complexity, but not so much that everything is constantly being scorched. The spaces in between are what make long-term stability possible. By looking at the dangers of the cosmos through the lenses of distance, volume and probability, we trade a little of our instinctive fear for a more grounded awe. The universe is dangerous in principle and mostly safe in practice, at least on the scales that matter for our lives. Our existence is still fragile and temporary, but it is not hanging by a thread over an abyss of constant catastrophe. It is resting on a platform built from light years of empty space, and the fact that most extreme events, most of the time, happen far away. In the final part of this journey, we will pull together everything we have seen and ask what it means to be a small, conscious patch of matter in such a universe. We will revisit the ancient fear of the dark, the modern fear of cosmic disasters, and see how they both fit into a larger story about curiosity, perspective, and the fragile, beautiful moment we're living through right now. We have walked a strange road together. We started with a peaceful night sky, then peeled it back to find storms on our own star, flaring magnetars, wandering black holes, jets from galactic hearts, bursts that light up the universe, and even the possibility that the vacuum itself is not the final word. It is a lot to carry in one mind. Somewhere in the middle of all that, you might have felt a quiet question forming. If the universe is this wild, how are we still here? And what are we supposed to do with that knowledge? To answer that, it helps to remember where our fear came from in the first place. For almost all of human history, danger meant nearby things. Teeth in the dark, a cliff edge, a storm rolling over a village. Our brains evolved to spot patterns that could kill us within seconds or hours. Those same circuits are still running when you hear about a gamma-ray burst or a rogue planet. They try to treat a threat billions of light years away as if it were a shadow behind the next tree. No wonder they sometimes misfire. Yet those ancient circuits did something else that might be even more important. They made us curious. The line between what is that noise and what is that light is very thin. The urge to reduce fear by understanding is the same urge that led people to map the stars, to watch eclipses, to track comets, and eventually to build telescopes and detectors that can sense gravitational waves. We did not just crouch in caves and shiver at the sky. We climbed out and started asking questions that reach all the way to magnetars and vacuum decay. Science, in that sense, is not just a pile of facts. It is a way of turning shapeless dread into something we can hold and examine. A solar storm stops being a mythical anger of the sun and becomes a coronal mass ejection that we can monitor and prepare for. A gamma ray burst stops being a vague space ray and becomes a rare, narrow jet from a collapsing star, with a calculable chance of ever harming Earth. Vacuum decay shifts from pure cosmic horror to a question about the Higgs field, with timescales so long that they dissolve back into philosophy. Knowledge does not remove every danger, but it strips away the part that comes from not knowing where to look. Along the way, we discovered something unexpected about these so-called threats. Almost all of them are creative as well as destructive. Supernovae and hypernovae tear stars apart, but they also forge the heavy elements that make up planets and people. Neutron star mergers can sterilize unlucky worlds, yet they are also the factories where gold and platinum are born. Even the growth of supermassive black holes, violent as it can be, helps regulate star formation in galaxies and lights up the distant universe so we can map it. The cosmos builds with the same tools it uses to break. Our particular situation turns that double-edged nature into a gift. We orbit a stable star in a quiet arm of a galaxy that is not currently tearing itself apart. We are far from active nuclei and known magnetars, far from dense clusters where stellar flybys are common, far from the huge voids where there is too little matter for richness. We live in a pocket that is balanced between chaos and boredom, enough activity to seed us with complex chemistry and energy, enough emptiness and distance to keep the worst blasts and collisions at arm's length. None of this required purpose. The universe did not arrange itself to protect one small planet. What happened instead is that in a cosmos big enough and old enough, some regions inevitably end up like this. Stars like the Sun form and live long lives. Planets settle into stable orbits. Chemistry has time to play. Given trillions of dice rolls, some land in the narrow range that can support complex life. We are sitting on one of those rare throws, looking back at the dice and wondering how they came up this way. The truly astonishing part is not just that we exist, but that we have started to understand our situation. In a moment that is a flicker compared to the lifespan of our galaxy, we have gone from seeing a handful of wandering lights to measuring the spin of black holes and the afterglow of kilinovae. We have turned tiny tremors in laser beams into evidence for colliding neutron stars. We have read the fingerprints of distant gas clouds in the light of quasars. We have taken our old fear of the dark and used it as fuel to illuminate the dark itself. That perspective can push you toward two very different emotional places. One is a kind of cosmic shrug. If everything ends in heat death or some other distant fate, if the universe is indifferent and we are the product of accidents, then nothing matters. The other is quieter and, in a way, braver. In that view, the lack of built-in meaning does not erase value. It creates it. A universe that does not care still allows for caring beings. A cosmos that will one day fall silent still contains this moment, where you can think, feel, love, build, and look up at the sky with wonder. The dangers we have explored sharpen that feeling rather than erasing it. Knowing that magnetars exist makes the quiet reliability of our own star more precious. Knowing that rogue planets drift in endless night makes each sunrise sweeter. Knowing that gamma ray bursts and kilonovae reshuffle matter on scales far beyond us makes the stability of your own life feel less like a given and more like a fragile, remarkable arrangement. Awareness of what could erase us is not a reason to despair. It is a reason to savour the fact that right now we are not erased. There is also a responsibility hidden in that realisation. We are one of the few known ways in which the universe has become aware of itself. On at least one planet, matter has organised into a pattern that can look back at the cosmos, build models of it, and feel emotions about what it finds. That pattern is not guaranteed to survive. It depends on decisions about how we treat our own world, how we handle technology, how we respond to real risks close to home. The big cosmic threats are mostly held at bay by distance. The nearer human-made ones are not. So what does it mean to live well in a dangerous universe? It probably does not mean obsessing over every low-probability scenario. It might mean learning enough science to see which dangers are worth preparing for and which belong more to thought experiments. It might mean supporting the quiet work of people who watch the sun, track asteroids, and design better infrastructure. It certainly means making room for awe, because awe is one of the few honest responses to the fact that you exist at all in a universe that could so easily have been sterile rock and thin radiation forever. When you step outside on a clear night after all this, the stars have not changed. The Milky Way still arches overhead. The same constellations still climb and sink with the seasons. What has changed is your sense of what those lights represent. Somewhere among them are dead suns, flaring magnetars, merging neutron stars and black holes silently bending the paths of photons. Somewhere far beyond them, the cosmic web stretches out, and the distant future waits in a long, slow drift towards simplicity. And here you are, on a small, warm world that has so far slipped between most of the cracks. If there is a single message in this tour, it is not that the universe is out to get you. It is that the universe is vast, indifferent, creative, and occasionally violent, and that within all of that, you have a brief, improbable window to be conscious and curious. You do not need perfect safety to make that window worthwhile. You just need enough time to look up, ask questions, and maybe leave a little more understanding behind than you found. In a cosmos where black holes can swallow stars and the vacuum itself might one day change its mind, that is already a quiet, extraordinary victory,